Okay, what's the problem with subset selection? As we have already discussed, it's problematic when you have high dimension, or when the number of features is greater than 20. It is like very difficult to do the computation. It's almost impossible, right? So best subset selection is impossible when p is greater than 20, and that's where you're going to use what is known as stepwise selection. And there are three types of stepwise selection. One is forward stepwise approach, backward stepwise approach, and then third one is hybrid approach. So the forward stepwise approach is like this. You start with a null model and then you keep on adding predictors or features to the model one at a time. This is important to remember. And choose the best model among the best of k based on RSS. Okay. Now you remember how you took k, right? When k equal to k equal to 1, you have p number of models, right? Because with x1 you can have one model, with x2 you can have one model, to xp you can have another. So you have p number of models in such way. So one of these models will be the best, right? When k equal to 2, then you take two variables at a time, x1, x2, then x1, x3, and so on. And then we'll have one model from that, right? So we have shown that here in this table. So when a one variable model, let's say x1 is the one that gives you the best model. Okay. Now what happens is, if that gives the best model, then that is retained in the model. It never gets dropped. Okay. So in forward stepwise, you retain that model, and it's highlighted in in bold. Okay. When it's a two variable model, subset selection gives you x1 and x3. Okay. In forward, we just added x2 and saw whether that is actually working fine or not, because for a two variable model, x1, x2 does a good job. So we just added x2, and once that retains in the model, that never gets dropped. So in the third model we have x1, x2, but x3 was not part of it, which directly went ahead with x4. And the fourth model with four number of variables, you can see x1, x2, x4 and x5. Okay, so there is no x3. So x3 got dropped here, and you do not have x3. So x3 did not meet what is known as an entry criteria. Okay, but that's not the case in subset selection. In subset selection, you can see variables having different selection. Like in one variable case you have x1, in two variable case you have x1, x3, in three variable case you have x3, x1, x3, x4, in fourth variable case you have x1, x2, x3, and x5. So what happens is that a variable can be part of it, or it can be not part of in the next model. Whereas in forward stepwise selection, if it is there in one variable selection, it will definitely be there in two variable selection, right? Now if you look at subset selection here, x4 is there part of three variable model, but it's not part of four variable model. So that will never happen. It's not part of variable. You can see there's no x4 here, but here with three variable it's there, but that will never happen in forward stepwise. In forward stepwise, you can see if it's their part of the three variable model, all three variable x1, x2 and x4 are a part of four variable model. Here you can see x1, x2 and x4. They're all part of the fourth variable model. So here three variable model is just a subset of four variable model. Second two variable model is a subset of three variable model, and one variable model is just a subset of two variable model. So that's the difference. Slightly confusing, but when we actually do it, it is going to be clearer. In forward stepwise, the selection is constrained, because you cannot have just random selection of variables. You cannot have just x1 with x2 and so on, and then x1 with x3. If x2 is there in the previous model, it has to be there in the next model. So then what happens is that you already have x1, x2. So the only selection that you will be making in the three variable model is that just choose whether it's x3 or whether it's going to be x4 or x5. So the number has come down, right? Because it's constrained now. The first two places is already taken because it's coming from the second variable model, right? But in subset selection, you can have any any combination, and that could be a number of uh, such cases. So less candidate models are there for selection, and it comes down to, instead of exponential number where it was p2 to the power p, as we have seen in the subset selection. Now it has come down to 1 plus p multiplied to p plus 1 divided by 2. So this is much less compared to this one. Sorry. So this is very high dimension compared to this one, especially for given p greater than 20. This is very easy, right? So when p equal to 10, in stepwise that we just discussed, in forward stepwise, we have 211 model, whereas in subset selection, just because you have just too many combination and there is no constraint, right? So remember the constraint we talked about, that the third variable model has to be the subset of the fourth variable model. Similarly, the second variable model is the subset of third variable model, right? That constraint is not there. Hence, in subset selection, we have over a million models. So estimating million models is very tough, whereas estimating 211 models is comparatively much easier, right? That's why forward stepwise regression model is preferred for variable selection, especially in given in high dimension. But if you have smaller number of dimension, let's say p equal to 5, you can always go ahead with subset selection. It's much easier. Then backward stepwise regression. Okay, so this is one type of selection method, variable selection method, which is reverse of forward. You start with all predictors and then you drop one at a time. So in forward, we start with one, then you go to two variable model, three variable model, and so on. And it's just the opposite. You start with p number of variables and then p minus 1, p minus 2, and so on. So here is a comparison. We have backward stepwise, we have forward stepwise. So you start with all the predictors available. Let's say you have 5 predictors, x1, x2, x3, x4, x5. Now here in the first step, we found out that x2 is a bad variable or not so important or the least important variable. It gets dropped here. So we have x1, x3, x4, and x5. If a variable is dropped, it never gets added again. Okay. So in the 4 variable model, you find that x2 will never be there, right? So you cannot have a 4 variable model with the presence of x2. So that's also a constraint, right? This is also a constraint. So you cannot have a 3 variable model where x4 has been dropped from the 4th variable model. So you cannot have x4, a combination of x4 in the 3 variable model. So that is constraint out, or that is taken out from the selection itself, and that's a constraint. So the number comes down. Similarly, for second variable model, x3 cannot be part of it because x3 gets dropped in third variable model. So here x5 gets dropped, so it cannot be present in the one variable model. So in the one variable model, you ideally should have 5 models, right, as per the subset selection. But here you will only have x1 with x2 with x3 and with x4. You cannot have a model with x5 because it's not part of it. I'm sorry, I'm really sorry. So it cannot have x2 either, you cannot have x4 either, you cannot have x3 either. You only have x1 because these variables have been dropped previously, right? So x2 has been dropped in the first one, x4 has been dropped in the second, x3 has been. So you cannot have 4 models or 5 models. You can only have x1 because x1 is the one that is never dropped in the previous times, right? In the last 3 or 4 steps, x1 hasn't been dropped. So in the final model, you can only have one choice or one model in that case. On the other hand, forward, you just do the exact opposite, right? You start with one model and then keep that variable, and then add another variable. Okay, so in 2 variable model, x1 has to be there. In 3 variable model, x1 and x2, which have been retained in this 2 variable model, has to be there in the 3 variable model. So you can see this is definitely there. So it's exactly the opposite of backward. So computational power requirement is similar to that of forward. Okay, and the selection method is through RSS and Debians that we have discussed. And the comparison between forward and backward is that you have more choices now. So you build a model with backward approach, you build a model with forward approach, and then you take the final model from backward and take the final model from forward, and then compare their, do the cross validation with test data and see which one is doing it, giving you the best prediction, and just take that as the final model. Okay, so you can also combine forward and backward, and it combines the features from both types. Okay, in forward you have variable which is included never drops out, right, in the next step. In backward, a variable already dropped from the model never shows up in the model again, right? If one variable has been dropped in the first step, it will never show up in the second step. Similarly, if one variable has been added in the first step, it never drops. It has to be there in the next step. So it combines. So hybrid model combines both. Okay. So hybrid starts with adding one variable at a time, like forward, but drop variables during the process. Okay. And if a variable gets dropped, it never shows up again. So it combines the features of both, or the qualities of both this type, forward and backward. Okay, so it's more like subset selection. So it takes more combinations, right? So it's more like subset selection, which takes both forward and backward approach, but it has the it has the computational advantage. That means it's not as computationally intensive as that of subset selections. So instead of using subset selection, you can instead use hybrid, which does more or less like subset selection but with less computational requirement. How do you choose the best model? Okay, once you have, now we have gone through several such steps of selecting variables, right? How do you choose the best one of them? Cross validation, right? And there are several of them. You can use k4, you can use leave one out cross validation, you can use bootstrapping as well, um, and the metrics that one should use could be R square, the AIC and BIC. You can use confusion metrics in the case of classification, accuracy, and so on, concordance, and so on. So there are several of them depending on the problem that you are working, the industry that you're working with. You have several different metrics to choose from. Okay, now we'll take an example. Now that we have some idea about the theory, we'll take an example to understand it better. So we'll take a data set, and we're going to use this data set, and we'll demonstrate these algorithms and see how it works. So we have this heater data. So there are several variables we have. So it's about the salary of baseball players in US, and it depends on many things. It depends on the different aspects of the players, and the different different predictors which predict the salary, which is the target variable for the given basketball player, okay, or the NBA player. Now we're going to use first subset selection, okay, and we're going to use this function reg subset, which will do the subset selection for us, okay. And then we'll see the summary statistics, we'll see the R square values, and we'll plot the BIC values, the Bayesian information criteria. We can also do the archaic information criteria or squash Bayesian criteria. So this will help us selecting the best model. Okay. Now it's very simple, syntax is very simple, right? You can see the function is rec subsets and salary is the target, and we are going to use all 19 variables. Probably we have used 8, I'm sure. I'm not sure whether it's okay. If I going to use all variables, you have to give a maximum, otherwise it's going to keep it down actually. Okay, because if you have large data set, the computational power is going to be massive. Given that it's a small data set, we can actually use 19 variables, which is okay. But if it's a large data set, it's going to be, so that's why it restricts to only 8 variables. I'm not sure whether I've used 19 or 8, but let's see. So it was 8 actually. Okay, I can extend it to 19, not a big deal. Okay, so you can see when k equal to 1, so one variable model, you will have 8 different models, right, with each one of these variables in place. Okay, now you can see out of this 8, this gives the best model. So from the first, when k equal to 1, you have the best model with CRBI. So your salary is best predicted as a function of CRBI. So that's one of the predictors or features. Okay. When you have two variables, models, you have many number of models, right? When k equal to 2, so you can see star over here, hits, and then CRBI. So when you have two variable model, the best prediction is given by the function of CRBI and then hits. Okay. When you have three variable model, you have hits and then you have CRBI and then you have putouts. Okay. When you have four variable models, you have hits, you have CRBI, you have division, and you have putouts. Okay, so that's the way it goes to 8 variable model. There are total 19 of them. You can actually extend that to 19. So for that, you just have to use this syntax, nvmax. Okay, and then out of the 19 finalized model, you have to choose what is the best one. Okay, how do you do that? Simply do the r square, just plot the r square, adjusted r square. Okay, and we'll do that for test data, not for training data. Okay, so when you do that, you get r squares values. So here we have taken training data, not test data. If you have test data in place, you better do it on test data. But even if you don't have a presence of test data, you have smaller data set and you can't divide into training and test data, still you can use. When you do a summary statistic, you can see the r square value is actually going up with more number of variables. So that actually is failing us. This actually is disappointing us by saying that we are using subset selection for bringing down the number of features. Because if that's the case, the prediction power is going up with adding more number of variables. So adding more number of variables is actually good. That's so ideally is the thought process. However, this can be validated by plotting the BIC value, and that's where we have done. So we have plotted the BIC value. So wherever you see the BIC, this dark spot actually touching, you see this is one case, this is one, second, third, fourth, 5, 6 or 7. Okay, I think 6 or 7. So either 6 variables or 7 variables is actually giving you the best model with a good interpretation. So BIC actually penalize you for having more number of variables. Okay, so with this plot you can actually find out what is the best model. Remember, this is all required when you are using training data for validation, which is actually not the ideal thing to do. But you already have a test data, you need not do this. What you need to do is that just calculate the the root mean square error, the RMSE, for the test data set for each model. So for each model over here, okay, you have 8 models, right? For 8 models, calculate the RMSE for test data for each 8 models and choose the one that gives the least RMSE. Okay, so the idea here is minimum of for RMSE. Okay, so that's the idea. Okay, now we'll compare forward and backward. So we just started with subset selection. We'll do forward and backward. Syntax is same except the fact that when you do not use any method, by default it takes subset selection. When you use methods forward, it is going to do forward selection. When it's going to use method, syntax is wrong slightly, is method me backward, then it's going to give you backward regression results, and that's what we are going to see. So here you can see that if something is added, like this is the forward one, if something is added, it never gets dropped. Now you will see CRBI has been added in the first model. When k equal to 1, you have CRBI in the model. Now you can see CRBI is there in all models. Now you can see it's star in all models, right? And that's the beauty of forward selection. It constrains that in all selection, all types of model, this has to be there. But you see that's not the case in subset selection. In subset selection, you can see CRBI is there in first model, in definitely in second model, third model, fourth model, fifth, sixth, but not in seventh model. You can see this is blank. Not in eighth model as well. Okay, because it can have any type of combination. So that constraint is not there. Whereas in forward selection, if a model is added in the first case, when k equal to 1, CRBI is the one that is giving the best model, that will be there in all the subsequent models. And that's what has happened. In the second model, you can see hits get added, right? And you can see in the subsequent models, in all subsequent models, you have hits as one of the independent variable, one of the features. Similarly, the third model, you can see what is there in third model. Okay, we'll see here. So in third model, put out is there. So you can see in all subsequent models, put out will be there. Okay, so that's the main idea behind forward selection. Okay, so again, if you're using training dataset, just look at the BIC plot and see in how many cases it's giving you the best prediction, and then choose the one. Otherwise, you'll have monotonic relationship. That means your ask query will simply be improving over number of with increasing number of features. So BIC plot is going to tell you what is the best set. But if you have test data in place, just easy, right? Calculate RMSE and find out what is the minimum RMSE for which set of models, which set of predictors you have minimum RMSE, right? So it might happen that it may not be just final 8 variables, it could be 6 or 7, which is less. So few variable gets dropped. That's the idea here. Some variables get dropped from the model.